So today we will discuss what is the conditions for the real roots of the equation f of fx is equal to 0, where fx is a simple quadratic in x. So let us say if fx is equal to x square plus bx plus c is equal to 0 for x is equal to alpha and beta. So this implies when fx is equal to alpha or beta. That means when fx becomes equal to alpha and beta, in that case, f of fx will be equal to 0. So in other words, you can say that the roots of this equation will exist, that is, we are talking about the real roots, will exist when fx is equal to either alpha or fx is equal to beta. So now let us see what will be the number of roots under these conditions. So let us go with the different possibilities. So first case, let alpha and beta does not belong to the real number. If they are not the real numbers, so in that case, that means fx does not have real roots. In this case, f of fx is equal to 0 will not have any real root. Okay, so f of fx will not have in that situation any real root if alpha and beta are not real. Now the second possibility is if alpha and beta are real but are equal roots. So let us say if alpha is equal to beta, fine, and they both are nothing but the real numbers. So this implies these roots has to be corresponding to the x coordinate of the vertex, which is nothing but minus b by 2. So in other words, this is the upward opening parabola and touching the x-axis at the vertex whose x coordinate is minus b by 2 and the y coordinate is 0. So we can say that this implies f of fx will be equal to 0 only when fx is equal to minus b by 2. Now, when does fx is minus b by 2? So, let us consider the different possibility with respect to this. First case, let us say b is some value which is greater than 0. So, if b is greater than 0, this implies minus b by 2a is negative, or fx which is equal to minus b by 2a has to be negative. But over here you can see that once we talk about the repeated root, fx is always greater than or equal to 0. That way this is never possible. So in other words, you can say that f of fx is equal to 0 does not have any real root. Okay, it does not have any real root. So if you can say vertex, at vertex the coefficient of x is positive, in that case f of fx does not have any real root. Now let us analyze the second case. So for that I'll just rub off the top portion. So please make note of it. I'll just rub off this portion. Pause the video and you can note down. I'll just clear up this. Now, second possibility, what we are talking about is what will happen if b is equal to 0. So when b is equal to 0, that means we are saying that f of 0, because the x coordinate of 0 is 0. Or in other words, b is equal to c, both are equal to 0. Or that means fx is nothing but x square. And then you can say that f of fx is nothing but x power 4 has only one distinct real root, that is 0, but all the 4 roots are real and all the 4 roots are nothing but 0, 0, 0. So you can say that 4 real and equal roots and only one distinct root. So this is what you'll have. Then lastly, if b is negative, so if b is negative, that means fx, which is equal to minus b by 2, because for roots to exist, it is must that fx is equal to minus b by 2. If b is negative, that means this is positive. So here we are talking about when does fx is equal to minus b by 2. If it is positive, let us say this is the line which is minus b by 2. So it becomes equal corresponding to x1 and x2. So this implies f of fx is equal to 0 has real roots, which is nothing but x is equal to x1 and x2. So you can say that, and both will be the repeated root. Both are repeated root. So all 4 roots are real, all real roots, but 2 distinct roots. 2 distinct. Because both are repeated root. Okay. So this is what you'll have. So this is once the fx itself has a repeated root. So that is the case. Now let us say once fx has 2 distinct real roots, then what it will be. So I'll just clear up this. You can pause the video and note down. So now let us look into the third possibility. Once fx has 2 roots which are real and distinct, that means fx, which is equal to x square plus bx plus c, is equal to 0 for x is equal to alpha, which is less than beta. That means this time our fx has this behavior. That is, it is cut by the x-axis at 2 distinct points, alpha and beta. And let us say the lowermost point, which is the vertex, the x coordinate of this is, let me write it here. The x coordinate of this is minus b by 2. And the y coordinate, let me call it as v of y. Okay. So now alpha and beta, that means f alpha and f beta is 0. Again, you have got the multiple conditions in this. F of fx will be equal to 0 when fx is equal to alpha or fx is equal to beta. So the first case is, let us say alpha is which is less than beta and they both are less than y coordinate of point V. So if they both are less than the y coordinate of point V, that means if I draw the line y is equal to alpha and y equal to beta, remember that means these lines are not going to, this is y is equal to alpha, this is y is equal to beta, and this is our y is equal to y of V. So hence you can see that this does not intersect this curve y is equal to fx. That means fx can never be equal to alpha, fx cannot be equal to beta. So in this case, fx cannot be equal to alpha or fx cannot be equal to beta. So this implies f of fx is equal to 0 has complex roots. So all 4 roots are complex. Then second possibility, if alpha which is less than beta is equal to y coordinate of V, that means now this time if I say that our this value is beta, so in that case fx is not equal to alpha, that means corresponding to this, you can say f of fx is equal to 0 will have two complex roots, whereas fx is equal to beta, because the y coordinate of the vertex is same as beta, so that will give us the intersection of these two will be nothing but the repeated root. So this implies f of fx is equal to 0 will have repeated root, and this root will be nothing but minus b by 2. Okay, that is nothing but the y coordinate of this point, which is nothing but equal to you can say that this is nothing but corresponding to this point, that is minus b by 2a. So that is x is equal to minus b by 2 will be the root. So hence you can say, and remember that this will be the repeated root of this equation. So if I talk about f of fx is equal to 0 has two real roots and which are repeated roots and two complex roots. So if we talk about distinct real root, there will be only one distinct real root. If it is one, truly speaking, we don't say distinct. Fine, you can say that does not have two distinct real roots. Then the third condition, if beta is greater than y of v, so let me rub off this portion. Now let us see the third case, that is if alpha is less than y of v and this is less than beta. Now once again, that means we have a line which is nothing but y is equal to alpha, and another line is y is equal to beta, which is above this, and corresponding to beta you got the values x1 and x2 on the graph. So hence we can say that this implies f of fx will be equal to 0 when fx is equal to, we know that the roots exist when fx is equal to alpha or beta, because whereas fx cannot be equal to alpha, whereas fx can be equal to beta, and when fx is equal to beta, fine, there are two possible values of x, that is x1 and x2, which are distinct. So hence we can say that that is f of fx is equal to 0 has two real and distinct roots and two complex roots. This is what you will have. Then the next possibility, I'll just rub off this portion. Now next possibility, if alpha become equal to the y coordinate of v and that is less than beta. So in this situation, what will happen is, let us say this is the graph of fx and has two distinct roots, alpha and beta, and this is the y coordinate of vertex, which is y is equal to y of v, which is also equal to alpha, and beta is above this, this is y is equal to beta. So this value is corresponding to minus b by 2, and this one is x1 and this one is x2. So now you can see that if we talk about the roots of the equation, f of fx is equal to 0. Now fx is equal to alpha for x is equal to minus b by 2 And this will be a repeated root. Is repeated root. And fx is equal to beta for x is equal to x1 and x2. So hence you can say that f of fx is equal to 0 has 4 real roots, whereas there are 3 distinct real roots. So the condition for 3 distinct real roots is one of the root should exist corresponding to the vertex of the parabola. Okay, and the second root, that is fx, should be equal to minus b by 2a, that is corresponding to the vertex of the parabola. And another is fx is equal to beta, where beta is greater than alpha. That is what you'll have. So now let us see. So that will be the condition for 3 distinct roots. Now let us see what will be the condition for 4 distinct roots. So once again, I will rub off this C part. Now let us look into the last part. That is, once we say that y of v is less than alpha, which is less than beta. That means we have a parabola. We redraw this, which intersect the x-axis at alpha and beta. And this is our y of v. And you can say that this line is y of alpha and this line is y of beta. And let us assume this value is x1. This value, it is not matching exactly at alpha. It will be some other, you can say x2. This is x3 and this is x4. Okay. So now here you can see that what will happen to our f of fx will be equal to 0 when fx is equal to alpha. This implies x is equal to x2 and x3, and fx is equal to beta. This implies x is equal to x1 and x4. So hence you can say that the condition, that is, this is that condition. So this will lead us to the f of fx equal to 0 has 4 real and distinct roots. Okay, so this is how we can say that what will be the number of real roots of the equation f of fx is equal to 0 based on the roots of the fx and what is the position of that root with respect to the y coordinate of the vertex of that parabola fx. Right? So this we stop here today.